I'm going to discuss the dynamics of anisotropic compact stars in rainbow gravity, which is about theory of gravity. Here is some plan, introduction, then a little bit of little literature review, problems and the results, and afterwards conclusion. So, as we all know, that there are two major and big theories to understand this universe. One is the theory of relativity, which deals with very big structures, including masses and energies of stellar objects. And the other major theory is quantum mechanics, and it deals with very small structures, including masses and energy of atomic and subatomic at atomic and subatomic scale. So, to understand the processes which are happening in this universe very well, we need a theory which lies in between these. And one of such developed theories is the theory of rainbow gravity. So it is considered to be a bridge between general relativity and quantum theory of quantum mechanics, and it is a very powerful in gravitational fields. And in very powerful gravitational fields and supermassive objects, they bend light and other electromagnetic radiations differently depending on their color, which is analogous to the electromagnetic wavelength, or more properly, according to the energy level. So this phenomena is imperceptible in the relatively low gravities, such as at Earth, but it is very much significant in extremely high gravities, for example, in the surroundings of the black hole or other compact objects. So according to the theory of rainbow gravity, the space does not exist below a certain minimum length, known as Planck's length, and time does not exist below a certain minimum time interval, Planck's interval, and all objects existing in space and occurring at the time, they do not exist below a certain length and certain time interval. So the medium of the space-time is always energy dependent, and it is specifically dependent on the energy of the probing particle. The high energy of the universe would have resulted in a different space-time curvature than current models predict, and the singularity of the Big Bang, it goes away. So it is the difference. So there are some basic constants in the theory of rainbow gravity: Planck's length, Planck's time, Planck energy, and Planck's mass. And mass energy relationship in rainbow gravity is E square F square minus P square D square, where F equals to m square, where E is the energy of the probing particle, and EP is the Planck's energy. F and G both are rainbow parameters. P is the momentum of the particle, and M is the mass. So now a line element we used to take in rainbow gravity, which is spherical symmetric static, is dS square equals to A square over F square dt square minus 1 over G square B square dx1 square plus L square dx2 square plus M square dx3 square, where A and B are functions of space and time. And three types of rainbow functions are used instead of this F and G. The first was given in 1997. F equals to 1 and G equals to 1 minus E over E raised to eta under root. And the second one, F equals to eta E by EP minus 1 over eta E by EP, and G equals to 1. And the third set was F equals to G equals to 1 over 1 minus eta E over EP, where eta is an rainbow parameter. So we can get general relativity as a restricted form of rainbow gravity when in the limit E by EP goes to 0, we get the rainbow function equal to 1. We reveal the general relativity. So as we all know that compact stars are the second densest object in nature. I'm taking it different from black hole, That's why it is the second densest object in nature. And they have very high mass as compared to their radius. And these include white dwarfs, neutron stars, and pulsars, and hybrid stars, or quark stars, strange stars, etc. And they may emit very huge magnetic field. They are born as a result of supernova, which is a very complex and the word often is here due to the fact that nowadays we know about the zombie stars and vampire stars. Thus, they are called these compact stars are the stellar remnants, and these have a state and type of a stellar remnant as a stellar remnant. Their state and type it depends on the initial mass from the star with which it has formed. And we usually judge physical features of these anisotropic compact stars. They have no singularity in the interior as well as on the surface, and they going out towards their surface. And the first derivative and of density, pressure, and if there is some tension regarding to radius should be 0 at the center, whereas second derivative should be negative for the whole mass distribution. And the anisotropy should be 0 at the center, and surface redshift should be positive and finite. So the special symmetric line element for the compact object is given over here as ds square, and it expresses the geometry of the white dwarf, neutron stars, and strange stars. This metric has no singularity in it, and what I have taken is the Carori-Brewer ansatz for these objects as mu equals to ar square and mu equals to br square plus c, and this ansatz it ensures that the gravitational potential and their derivatives they are finite at the center. So the Carori-Brewer line element in the rainbow gravity is given as ds square in this slide, and the pair of rainbow parameters which I use in my work is f equals to 1, g equals to 1 minus e by p raised by theta whole under root. So for the anisotropic distribution, I have taken the string theory tensor, and this is the energy momentum tensor. Perfect fluid. And the second part is minus m x nu, where minus m is the string tension, and these strings are associated with the particles of perfect fluid. And when f equals to 0, that is the string tension vanishes, this energy momentum tensor becomes of that of perfect fluid. And when I take p equals to 0, that is when I take pressure equals to 0, it becomes of the energy momentum tensor of the cloud of strings. So many people have worked on such objects and on the dynamics of these objects. Mustafa Chang and Shami, they discussed anisotropic distribution with linear equation of state in the star gravity, and they validate their work while working on specific compact objects. And there are many others which are shown on the slide. They have worked in different fluids with different fluids and different equation of state in general relativity, in the star theory, and other theories. These are the recent works, but no one has done this. So my objective was to discuss the dynamical variables from the field equation and to discuss the physical acceptance of the resulting compact objects. So here are the field equations and Einstein field equations, and when I substitute the values from the metric and the energy momentum tensor, I got these three equations. And when I solved these equations, I got the mass density given over here. And as you all can see, that mass is maximum at the center and gradually it decreases by going towards the outer surface of the compact star. The pressure over here, showing the same thing, that the pressure is maximum in the center and it is gradually decreasing while going towards the outer surface. The strain tension, it is nearby zero in the center, but gradually decreases and then increases towards the outer surface. And then I calculated the energy conditions for this matter tensor, which are shown over here: the weak energy condition, the other energy condition, and strong energy condition. Substituting the values, the null energy condition, as we can see on the slide, is giving the positive results. The weak energy condition is also positive, and the expression for the strong energy condition is also giving positive term. So derivatives of energy, pressure, and tension. The first order derivative are all zero. The second are all negative. The anisotropic factor is over here. The mass function is calculated. The compactification factor is showing some physical results as well as the redshift. So we have seen that all the physical properties for the compact stars are satisfied by the model. Thus, the physical acceptance for the